So today I'm going to speak on behalf of two of my students, Matt Rogan and Sam Schaefer, and also my colleague, Dr. Preswell Moreno, who will actually also discuss the topic, some of the topic in a minute. I'm going to discuss Poro-Elastic modeling of corroding reinforced concrete using an acoustic model, which is the Biot-Stoll model, and high frequency ultrasonics. And here's a little bit of background. So as you can see on this slide, we have a bridge over here at South Florida, where I'm from, and you actually can see some of the concrete damage on the piling. So in the marine environment, we have issues with corrosion, we have concrete structural damage, and associated with that, we have maintenance, repair, and cost. And one of the big things, and everybody knows it here, but just bring it up anyways, that Florida bridges are prone to chloride-induced corrosion once chloride threshold is reached. And in partially immersed bridges in marine environment, these ions are going to penetrate from the exposed surface into the rebar, is eventually causing so much corrosion that there is pitting, and in addition to that, there's going to be spalling. So there are techniques to prevent that, but Dr. Preswell will cover in more detail later. But really, the big thing for me, as far as my research is concerned, is that as the rebar slowly corrodes, and like you can see in the diagram from the top left to the center, first you have the rebar in the concrete before corrosion right here, and then as the corrosion evolves, there are these cracks that actually form within the concrete, causing eventually spalling. And so with all that, you all know that one of the techniques to actually monitor this type of issues is associated with ultrasonics. And even in fact, I was brought very justly earlier on, some of them are actually not even above 20 kilohertz, they're actually in the audible sound field. The fact is that ultrasonic non-destructive testing has been of great interest for decades. And one thing that has been happening is that many of these techniques, which actually are used, are either operated at maybe around 10 kilohertz or at hundreds of kilohertz. And this is what I'm focusing on today. And there are different signal processing techniques that are used, such as SFTF. There's a lot of work on neural networks, for example, ANN, CNN. We do a lot of work in wavelet decomposition, empirical mode decomposition, Laplace transforms. All these techniques are very well known and established, but they all share one thing, one problem in common, which is they all rely on a very simple model of sound propagation within the medium, and the ability to perform early crack detection depends entirely on spatial resolution. Now, I only have 15, not even that, 12 minutes to present everything. So I provided a lot of additional information on the slide where you can read later. I'm going to focus on the really important aspect. So limitation number one, dependence on spatial resolution for early crack detection. Limitation number two, early crack detection capability depends on the meaningful training of the crack detection algorithm. Limitation number three, early crack detection capability depends on the complexity of the sound propagation model. And this is where comes the work I've done. Sample observation clearly indicates that in the vicinity of the corrosion and crack, there is a complex structure combining fluid cavities and loose concrete material surrounding the corroded rebar, which means that a more appropriate acoustic propagation model would be the Poro-Elastic model, which actually accounts for the presence of an aggregate, a metal, and fluid in pores, or possibly gas, in fact. So the BO originally developed a model which is actually very commonly used in the field of sediment acoustics. It was expanded by Biot-Stoll, and then after that, I actually did quite a bit of work over the years based on the work from Stern to actually account for the gradual changes of the properties of the material as we go deeper and deeper, which is perfect to actually mimic the formation of early crack around the corroding rebar. One thing that's important is this is a frequency model base. So we actually model at every single frequency in ultrasonics the response of the rebar and the concrete, the reinforced concrete. So briefly, in terms of the problem statement, the Biot-Stoll model although it is complex, has the great benefit of tying the physical properties of the porous medium, such as porosity, mean grain diameter, mass density, bulk moduli, shear moduli, and so on, to the sound propagation through the medium. And in addition to this original model, I actually published, as a past author, based on the work by Stern, the ability to handle gradual change in the physical characteristics of the medium. Now, knowing this model exists, we can adapt the model to reinforced concrete problems and actually tie this to a nonlinear least square algorithm based, in our case, either I selected the truss region reflective model to actually fit the parameters of the Biot-Stoll model, which are physical parameter of the rebar, concrete, to what we actually measure. In short, the objectives are threefold: identify the proper measurement configuration and predict the performance using the modeling of the ultrasound propagation in the reinforced concrete. 2, to perform a series of targeted measurements using the proper ultrasonic transducer on a set of existing reinforced concrete samples. And 3, evaluate the degree of corrosion within the reinforced concrete with confidence level according to the Poro-Elastic model and TRR algorithm. And then we want to correlate these to other measurements, like the electric potential measurement that Dr. Preswell actually performs in his lab. Now, here is a diagram of the approach. Physically, the approach is much simpler than everything I've seen so far, where you have very heavy equipment. We just take concrete blocks, we put them in the water. We have an immersed ultrasonic transducer operating at 500 kilohertz. We transmit 7 microsecond long pulses, and we actually place the transducer from one place to the next along the rebar. This is a side view, this is a front view of the setup. So we pretty much place, and this is the trick, quite accurately the transducer right above the rebar and transmit a very narrow beam, high frequency cone of sound. And the approach associated with the processing is twofold. So we have the data acquisition, where we place the transducer at different position, acquire right now 10 records, perform some time synchronization and time averaging. And in purple, in salmon color over here, we actually, based on the default set of physical parameter, we actually calculate the theoretical noise-free response in the concrete, reinforced concrete and rebar using the Poro-Elastic model. We actually verify that the initial setting and the measurement produce at least a reasonable result. So where we start from something at least decent. Then after that, what we do is that we run the TRR algorithm when we let an intelligent algorithm, and it could be a convolutional neural network later on, but the TRR is a very powerful, well-established algorithm for this. So we actually let the physical parameter of the reinforced concrete fluctuate to see what is the best possible match, theoretically. And then after that, what we do is that we repeat the operation periodically. Right now, it's about every 4 months, where we actually take the same concrete but are slowly and happily corroding, and we actually repeat the operation, see if we actually observe a trend. That's what we do right now. Now, a few things that are important is that we are trying to track 2 phenomena, pre-cracking corrosion and post-cracking corrosion, with the understanding that the detection and identification of pre-cracking corrosion, which is actually possibly the most useful one, is also the most difficult one. The earlier we can actually spot various signs of cracking, the better it is for people who are actually doing preventing maintenance and other operations. Now, the idea behind pre-cracking and post-cracking is that we're going to observe changes in the characteristic impedance in the rebar, which is actually going to be observed in the frequency response of the ultrasonic transmission. And that's what we're actually going to do right here. We're going to monitor all this. How am I doing on time? 5 minutes. Okay, good. So that gives me a little bit of time to discuss some of the work accomplished here. We have 3, Dr. Preswell generously gave me 3 concrete samples from his lab, one that was really nice looking, another one that was showing early signs of crack, and one that's completely busted. And we repeated tests again and again, allowing for further corrosion using salty water over the course of about 8 months. And you can actually see the setup over here. It's very simple. We place as accurately as we can the transducer over the rebar, and we scan the rebar, and all the characteristics of the concrete sample is shown here, with the understanding that when we number the samples, sample 1 is the one with no sign of cracks, sample 3 is the one with a lot of cracks from left to right, and there are 2 rebars in each of the samples, which we monitor, a top and bottom rebar. So the way we actually perform our operation, we do all our data acquisition, we collect our raw data. Again, this is a low budget project, so this is not very sophisticated, but we use what we have and it works. So here you see a series of data collection after time averaging of this very high frequency signal. The strong signal is the echo coming from the surface of the concrete, and this very faint echo over here is that of the rebar. Now, we actually do this time acquisition. We time gate the signal to isolate the portion that consists of the surface concrete echo and the rebar, the first rebar echo over here. And the idea is that we do not just do timing, we actually match the signal. We run a model that recreate the signal that we should have measured with this type of transducer. The matches are not going to be perfect, but they actually lead to some very interesting results. Now, in the process of running the model, I'm not going to give you all the detail of the model because we could talk about it all day. It's a fairly sophisticated model, but you can see the number of parameters we can control. And these are physical parameters: bulk of moduli, shear moduli in the water, in the concrete, in the rebar. We can look at the Poisson ratio, and most importantly, we look at porosity and permeability, which I think are important parameters. I've seen some talk, and in fact, it will be very interesting to actually look at this technique for asphalt as well. Now I'm looking at some aspect of what you do in the field of asphalt study. So these are some of the parameters we're currently causing to vary. So the way is we start again from an initial guess based on what Dr. Persuel is telling us about, for example, the porosity of the system, and we allow this parameter to vary independently. And we actually use the TR algorithm, which is a sophisticated nonlinear matching algorithm, to actually find better matches in terms of the value for all these parameters. As study grows, we're actually going to cause every one of these parameters you see on the display to vary. But right now we have a subset of 7 parameters. So here is the original signal. In blue is the measured signal. In red is the original guess. As you can see, the match is not perfect, by far not. And this is what happened as we actually use the TR. It's another example of a signal. This is in red, the measurement. In green is the initial fit. And as we actually provide a wider and wider range of possible fluctuation of the parameter, it actually takes us to the blue curve, which is a better and better match. So this is where we are today. In addition to that, we run a lot of measurements now. We have hundreds and hundreds of tables for the different sample and rebar and the period of time. But what we're doing now, we are looking at the mean and standard deviation and the trend in the fluctuation of all these parameters to see if indeed we can actually observe, for example, an increase in porosity due to the presence of additional cracks. Okay, with that, where we are going to be going next is actually running additional measurement. And in fact, it was really interesting yesterday to see some of the talk, because I'm anxious to actually to have access to maybe a database of a measurement in a well-controlled environment where there are signs of corrosion in the rebar, possibly delamination. The technique I'm talking about can work for delamination. And the last thing I would like to bring up is that the technique I'm mentioning here can also work for oblique transmission transducer, like contact transducers, which are very often used for example, to observe delamination process and corrosion, corroding rebar. And that's the end of my talk. Any questions? Yes, sir.
Interesting talk. One question would be the spatial resolution of, like, how wide the crack needs to be.
Well, this is not about spatial resolution. At this point, this is about signal to noise ratio. We do not actually attempt to build an image of the echo. We while you actually saw 2 times signal, the echo on the surface and the echo from the rebar, we are truly matching the spectrum. So we are doing a spectral match between what the model says and what we actually observe. And so in terms of the resolution, if we had a perfect model and a very, very high signal to noise ratio, we would go well within a millimeter. The question is, how accurate is the model at matching the physical content of the material? You understand? This is in terms of resolution. This is what we are talking about is a super resolution system, where instead of actually trying to align peaks of energy in the echoes, we're actually matching the entire spectrum of the signal. So it would be sub-millimeter.
Sorry, a subsequent question.
Yes.
So the model is more like a statistic.
It's a pure physical model. The bio model actually modeled the granular structure of the concrete and the pore within the fluid. So, for example, depending on the shape of the grains, whether there is, for example, clay, or you have a grain of sand or aggregate, the shape and statistical orientation of the material is actually accounted for in terms of the mass loading and, for example, the permeability of the material. This is the parameter and the way the model is actually handling the concrete is very, very similar to some of the discussion I've seen before. So it's a purely physical model. Yes. Yes, sir.
I'm sorry, I missed the beginning. What was the frequency of?
Right now we operate at 500 kilohertz. This is an immersed transducer, but the oblique transmission transducer with surface wave could be handled by this model as well, because this model handles compressional wave and shear waves.
Do you observe any effects of scattering from aggregates?
That's an excellent question. In fact, if you actually look at it, we have some level of scattering. Scattering is a big issue, and when we use these high frequencies. And the truth is that the samples that Dr. Preswell gave me were actually, I would not call them aggregate free, but they had a lot of cement in it. So presence of large aggregate can actually cause a lot of oscillation and fluctuation. In fact, you can see it on this slide right here. It's pore. You see the echo at the surface. You see the echo from the rebar, and here we have actually some aggregates scattering.
At least those dry contact ultrasonic.
Yeah.
And the range 50 to 100 kilohertz. So I'm just wondering.
Oh yes, this is always a problem. When you actually go in the low frequency surface contact transducer, it's not so sensitive to it. This 500 kilohertz transducer can have can be a serious issue.
Very interesting. I think that we don't usually the case that if the rebar are close to space, the interference from the other rebar.
No. So first of all, the rebars, if you actually look at the diagram right quick over here, see in reality we have, I'll use my cursor over here. We actually have 2 rebars that are virtually aligned, and there is like a gap in the middle. So there is no, because we're on a vertical transmission, there is no rebar interference. However, what is there, which I did not have time to discuss, is that as the sound is transmitted and hits the rebar, there are secondary reflection from the bottom of the rebar and the bottom of the concrete block. But we use time gating and very short pulse, which actually allow us to separate between the different echoes. Does that answer your question?
Yeah.
I'd like to move on to our next speaker.
All right, thank you.